Alright, so in this video we're going to kick off our new unit on kinetics and specifically talk about reaction rate. So first let's quickly break down this word kinetics. If we think about the word kinetic, this means having to do with motion. So when we're talking about kinetics in this whole unit, we'll be studying the motion of molecules, but more specifically, the speed of molecules. And even more specific than that, the speed of reactions. How do we measure the speeds of different reactions qualitatively and qualitatively? How can we determine the steps of a reaction? And how can we affect the speed of a reaction? This is all under the term reaction rate. Remember, the word rate just means speed. So same exact thing. One thing to note, reaction you will often see abbreviated as RxN, just out of laziness and ease. So when we're talking about the reaction rate, let's say we have a reaction that's very simple. It's drawn right here. We have molecule A. Over time, molecule A collides with itself, and it turns into molecule B. So when we're measuring the reaction rate, what are we actually measuring? This is a definition that you need to know. The reaction rate is the change, delta, triangle, change in concentration of products or reactants over time. So when we're measuring the rate of a reaction, we're measuring either A, how fast the reactants are getting used up, or we're going to be measuring B, how fast the products are being made. There's two ways to measure it, because in any reaction, both are going to happen. The reactants are going to get used up, and the products will be made. So how does this look quantitatively? Again, if we were measuring the rate of a reaction, it's the change in concentration. So it's the change in, let's say we're doing the change of the products, concentration of B. Remember, refresher, these brackets mean molarity, over time. The change in time, delta T. So we can measure either the change in concentration of products over time or the change in reactants over time. Quick thing to think about, products, this is going to be a positive rate because products are being made. However, if we were to write the rate expression for the reactants, it would be negative concentration of A over change in time because the reactants are getting used up. The concentration is decreasing. What's another way of representing that? Well, here's a graph. On the y-axis here, we can see we have concentration in molarity. Again, those are our brackets. And this is our reaction A turning into B, where we start with all A, a concentration of 50 molar in this jar. And over time, those molecules of A are turning into B. So what's happening to the concentration of A? Well, it's dropping over time because A is getting turned into B, which starts at a concentration of 0 molar and slowly increases as those molecules from A get turned into B. And we can see that in the pictures as well. Over time, the purple dots, representing the molecules of A, are decreasing. And we're getting more and more green dots, which are representing the molecules of B. So what we'll need to do in class is talk about how to measure the rate quantitatively using actual numbers, but we also want to just keep conceptually in our minds what's happening to the amount of reactants. A, they're decreasing over time because they're getting used up, and they're being turned into products, so the concentration of the products will be increasing. Reactions only happen because of two main factors, and these fall under the umbrella of something called collision theory. This is the idea that explains what must be true for any chemical reaction to occur. So there's two things that must be true. Number one, molecules must have the correct orientation. What do I mean by orientation? Another word for orientation is direction. Molecules need to be facing the right way. So for example, here we have molecule A colliding with molecule BC. Okay? But as we can tell, in this example, A is facing B. And according to what I'm saying right now, that must be the correct orientation. Those molecules must be facing that direction in order, again, this is like our reactants and our products, in order to make our products, where B switches what it's bonded to, is now bonded to A and C is by itself. Let's say you took this molecule here and we flipped it around so that C was in the other direction. Now C is going towards A. Well, we can see here, no reaction occurs. So this is what we mean by orientation. We got to always remember that molecules are three-dimensional. They take up space. They face certain ways. And some ways will cause reactions to happen. Some ways they won't. Simple analogy. Think about making a peanut butter and jelly sandwich. And we did this in class in CP Chem. If you have a piece of bread, okay, with peanut butter on it, and another piece of bread with jelly on it, and you put them together like this, you're going to make a nice sandwich. The orientation is correct. However, if you took a piece of bread with peanut butter and a piece of bread with jelly on this side, and you put them together, that's not going to make you a very good sandwich. Okay? That reaction does not have, those molecules do not have the correct orientation. So, molecules have to have the right orientation for a reaction to occur. They also have to have enough energy for a reaction to occur. This is called the activation energy. Molecules must have enough energy to activate a reaction, to start a reaction. And we'll get into a lot more details about activation energy going forward, but what you need to walk away with right now is for any reaction to occur, molecules must have two things: the correct orientation and enough energy to make the reaction occur. Let's say you have a reaction. Vinegar, baking soda. And we did this in a lab in class with these little film canisters. When you mix these together, we know that bubbles are produced, and eventually, if you remember the lab, this lid blew off because the pressure got too high inside. So this reaction is happening because we have molecules of vinegar, which we'll draw in red, colliding with molecules of baking soda in green at the correct orientation and with enough energy. And that produces products. But let's say we wanted that reaction to happen faster or slower. What are some things that we could change in our experiment to make that reaction happen faster or slower? Three main things we're going to talk about right now. We'll add two more later. But number one, temperature. Let's say we took the vinegar and we heated it up. So instead of 50 degrees Celsius, it's now 100 degrees Celsius. If you increase the temperature, what is that going to do to the rate of the reaction? It is going to increase the reaction rate. They are directly related. Vice versa is also true. If you decrease the temperature, that's going to cause a slower reaction rate. What about surface area? What's true about surface area? Well, just a quick refresher, surface area. Let's say you have an M&M right here. Then you take that M&M and you crush it up into little M&M pieces. Okay? When you have more pieces of something, that equals more surface area, which I'm going to abbreviate SA. So this, a crushed up M&M, has more surface area than a whole M&M. So which of these would cause a faster reaction? Let's say you had two options. You could use like a cube of baking soda, or you could use powdered, crushed up baking soda. Which would have a faster reaction? Well, if you have more surface area, you increase the surface area, that's going to lead to a faster reaction rate. Again, opposite also true. Less surface area, slower reaction rate. Last but not least, what about concentration? Okay? Concentration is essentially the amount that you have. So if you have, 1 molar vinegar or 6 molar vinegar reacting with baking soda, which one's going to have a faster rate? Well, again, if you increase the concentration, you are going to increase the reaction rate. And the explanation for all three cases is the exact same. If you think back to what we know about reactions, collision theory, molecules need to have the correct orientation and energy for a reaction to occur. So in all three cases, we're either increasing the number of molecules or increasing the energy of the molecules, which is going to cause more reactions to occur. Temperature, molecules are moving around faster now, so they're going to collide more often with more energy, more reactions happening, faster rate. If we have more surface area, there's more pieces. There's more opportunities for collisions to happen between molecules, so the rate happens faster. Same thing with concentration. At a higher concentration, there's more molecules, more collisions, faster reaction rate. So what you need to be able to walk away with today, understanding the definition of reaction rates, as we outlined here in words, and being familiar with these type of representations of a rate, knowing how to interpret graphs that show us different rates of a reaction, understanding the two main parts of collision theory and what they mean, as well as the three ways to affect the rate of a chemical reaction.